This conference will now be recorded.
Okay, so good morning, everyone. Thank you for joining today. For today's session, we're going to have a guest speaker, Hisham Al-Bakouri. Hisham has been with TAP from the very first day, and he is an independent consultant in the industry, and he's going to give a talk about time synchronization in time-sensitive networks. But before we give the floor to Hisham, just a quick reminder that next week is the OCP Tech Week. There's a lot of exciting tracks, and of course, one of them is the OCP TAP track. This will happen for us on Thursday morning Pacific time, and I hope that we'll see everybody there. Us team, we're very busy in preparing the slides and the talks and the demos. So I hope you will all tune in, and we'll get your participation and your friends joining us next week. Without further ado, Hisham, would you like to kick it off?
You see my screen?
Yep. Yes, we can see your screen.
Oh, great. How I can minimize I can see how I can minimize this.
You can press Shift and F5. It will do the trick. That's a Windows system.
Because I see all this other things. Oh, Allah. Anyway, let me do this.
Yeah.
So, you see my screen now?
Yes.
Yep.
But I still see the GoToMeeting stuff. I don't know how to. Maybe this one.
We can see the screen perfectly on our side. So feel free to start when you're comfortable.
Okay, so today I am going. Do you hear me well now?
Yes.
Yes.
Excellent. So right now, today I'm going to talk about time synchronization in time-sensitive networking, TSN, and I hope we can get something useful for our work on defining the profile of BTB or 1588 for the data center. Oh, my screen doesn't move. Here it is. So the presentation is divided into two sections. First section is TSN introduction. We'll talk about brief history of TSN and the TSN quality of service tools and profiles, and its basic components, management model, and we will talk also about one tool in TSN which is used for scheduling traffic to leave egress interfaces from different switches or bridges in the time-sensitive networking at the right time. It's called IEEE 802.1 QBV. It is the time-aware shaper or scheduler. We'll see that how it works. We'll see how it works in action, and then I will conclude that section by having a brief discussion on the deterministic data center and how we can maybe benefit from what TSN group in IEEE 802.1 did in defining the profile for data center in this project, how even we can improve the whole data center performance using TSN tools. The second section will talk about a brief overview about 802.1 AS, which is the generalized BTP standard defined by the TSN working task group in IEEE 802.1. So let us start with the TSN introduction. So The whole TSN work started in 2005, actually. And it wasn't called TSN at that time in IEEE 802. It was the group, in actually in IEEE 802.3, the Ethernet group, to look at what can we do in IEEE 802 or Ethernet 2.3, which is Ethernet, to support audio and video traffic. First for the consumer, user, and then for the business or enterprises. And then later, that whole work moved to IEEE 802.1, and initially the group was called Audio Video Group because you were looking at what can Ethernet bridges can do in order to transport audio and video traffic, which is something that conventional Ethernet or traditional Ethernet cannot do. The traditional Ethernet actually cannot support applications with stringent timing requirements like providing deterministic and low latency. It cannot do that. So actually in 1998, we had a quality of service group to address this problem, but it didn't work out. It wasn't 7 years later in 2005, where because of the demand of the industry, IEEE 802 decided to do something about it, how we can support real-time application like audio video. And this is why the TSN, the audio video task group, started it in .3 first and then moved to IEEE 802.1. In 2012, there was demand from the industry to support time-sensitive applications for factory automation and then later for automotive industry. So the audio video group got renamed to the time-sensitive networking group. And the whole idea behind the time-sensitive networking group is really to address all these limitations in the traditional Ethernet, which is basically only provide best effort service. Now, Ethernet can provide deterministic low latency services and also can support real-time application like audio and video. And this whole thing, audio, video, and factory automation application and automotive applications, all of those applications are addressed now by the TSN task group. That's really just a quick history, and TSN task group is continuing. In fact, this week is a week for the plenary for the IEEE 802.1 task group, and it is still going full speed ahead because of the demands of the industry. So if you look at this slide, actually I got it from Janus, who is the chair of the TSN task group, and describe what the main pillars or fundamentals of TSN, which is tools to provide bounded latency latency, tools to support synchronization, which is IEEE 802.1 AS, the profile for 1588 to transport the time across a time-sensitive network, tools which support resource management like bandwidth reservation across the TSN network, supports reliability, which is done by one standard, actually IEEE 802.1 CB, which provide frame replication. So the frame can be sent into two routes or across the network, and if one of them fails, the other one will arrive, so you guarantee delivery of the frames. And it uses IEEE 802.1 CA, which is a protocol to preserve the route or the path within the layer 2 network that will be traversed by the frames sent across this network. And it reserves two of them. One, the frame will be sent into both of them, and then when both frames arrive, one of them will be eliminated by the recipient. If one of them didn't arrive, then at least the second one hopefully will make it. I personally have some reservation on using this kind of frame replication. I believe that we can use something like network coding to avoid frame replication altogether, and this will have the net effect of reducing bandwidth in the network as well as improving latency. So you can think of TSN as a group which creates tools to transport time-sensitive applications. And these tools, not all of them are used by every application. So some of these tools are used by some applications, others can used by some other applications. So we have something called TSN profiles, and a profile is a collection of tools to support a specific application. Of course, we started with audio video, so the first profile is to support audio video real-time applications. Then we had another profile to support front-to-hole, which is
Hisham?
TCL. Yes.
First, I want to say that we support this standard in the NIC, and we offload it completely, so we know. So there are hardware equipment that support it. But we are struggling to find someone that actually need it, because in the video, for example, most of the industry is using the SMPTE 2022-7, which is the same.
Yes. Yeah, but I'm not sure why. I know what NVIDIA is doing, and you guys participated in TSN. So you have some people participated from your group into the TSN. The TSN is actually gaining momentum in the industry, and I'm not saying it is. So it is deployment in the industry is increasing. There are other contenders, many other, especially for factory automation, many of them like Profinet and others. But TSN is gaining momentum, and I cannot really claim that it is now the best thing to be done, but it is definitely moving forward.
I was specifically talking about the 801.2CB, which
that's for reliability, right?
Yes. Which industry needs that? Use that?
I think they do, but I haven't seen big ways of using it. I agree.
Yeah.
And as I mentioned to you, and I agree with your observation, and I mentioned this to them, and I'm one of the people who really have some reservation about using .1CB. I would prefer. I did some work with Professor Morel Medard in MIT, where we proved that if we use network coding, we can avoid frame replication, and we can also, and by doing that, we can even improve whole bandwidth utilization as well as improving latency. So we did all the analysis. Unfortunately, Elad, I cannot publish it because it was done for my previous employer, FutureWay, but that is the net results. If you are interested, Elad, in NVIDIA or your group to pursue that, I can connect you with Professor Medard and you can work with her.
Hi, this is Alon from Keysight Technologies. I have a few comments if you don't mind.
No problem.
So first, to answer Elad's question about who's using this. So CB
it was actually Dotan. It was Dotan from NVIDIA, my colleague.
Oh, sorry. I'm sorry. It's being used in automotive and as well as some industrial, such as factory automation. And the reason they're using this instead of the other protocols, this is a layer 2 protocol and it's very simple to implement. But as was said, it's not the only choice. One of the Now, one of the things that these protocols are trying to deal with is they're not really trying to deal with packet loss as much as they're trying to deal with equipment loss as well. So that means, let's say, and so if you have a switch, that stops working, you will have zero packet loss due to that switch stopping working because you're sending things through two paths all the time. There's no switch over time. That's really the reason people are using this and similar algorithms. It's not the only way of doing it.
Yes, exactly. So yeah, anything happen on that path, link goes down, switch goes down, at least the backup one can be used and we guarantee that traffic will arrive. My concern is using bandwidth. If you send the frame twice, I don't like it. And some people, when I was attending IETF in the .NET group, the chair of the group actually, not Janus, the other one, agreed with me. And because of this, I started that work with Professor Morel Medard, and we proved it. We really proved it. But unfortunately, the TSN group is not, they have a mind of their own, and they don't want to change the standard now and all of this. But it is definitely an area for improvement. I'm one of the people who believe in network coding, and I think it's a better way of doing it. So, but thanks for the discussions. But again, we have all these profiles, one for industrial automation, and now we have automotive, which started last year. We have a new profile just approved, which is .1DF, and it's an ongoing project. All of this automotive and the service provider one are ongoing. They started and it's not done yet. As a matter of fact, even the industrial automation IEEE 60802, which is a joint work, is still going. I attended this morning their meeting as part of the plenary, still working on defining the profile for TSN profile for industrial automation. The service provider is mainly used for 5G, backhaul, and mid-haul. And that can be very useful actually for the new ITU project that defines a new transport for 5G. So, but don't confuse this with front haul. The .1CM is front haul. The .1DF is for service provider. Front haul mainly using frame preemption and just strict priorities, where service provider will be using other tools, including IEEE 802.1 QBV, which I will focus on it through the discussion. Oh, how I can. Doesn't move. Doesn't this one doesn't move?
Page down. Does page down work?
Doesn't move. Yeah, here it is. Anyway, that's good. Work it. You see my slide now? Hello?
Yes.
Yes, we do.
Good. This is how TSN network looks like. You have bridges, layer 2 bridges. Some of them support the TSN, some don't. And of course, if those guys don't support TSN, Shaper, Polyesters, all of these tools, we just do normal forwarding. But of course, in a factory, you would like all of them to support all of these tools to ensure that factory traffic, for example, from a listener to a talker, like from a sensor to an actuator, from a controller to a robot for motion control, for example, that will arrive on time. So you need all these bridges to support these tools. And then just a few, this simple slide about TSN management. TSN management is a mess. And I worked with a company last year and other companies actually to start to change TSN management to improve it and address many of its problems. Because it supports three models: the fully distributed model, where you don't have centralized controllers or centralized user configuration manager. You have fully distributed centralized, which has both of them, and you have a hybrid, which you can use the centralized network controller, the CNC, but it doesn't use the CUC. It's a mess. And but there is inclination now within the group to support the distributed model, where all the centralized stuff is not needed, although the centralized model has its own advantage, and it is now the one that is used. Some people try to use SCDN, software-defined networking, and replace CNC with an SCDN controller. There is some work that has been done in this area. But the reason I mentioned, I want to present this slide, is that I would like to show that the team here how a tool, which is IEEE 802.1 QBV, which is called time-aware shaper or time-aware scheduler. Shaping is scheduler. scheduling also. It's not work conserving. So and how it works. And QBV is good for a factory, because in a factory you would like all the traffic, especially maintenance and control traffic that is regular, to be, when it's sent from the talker, to arrive at the listener at some deadline. So there is deterministic latency, and it has to be very low as well. So QBV was designed to allow that happen, to ensure that traffic from each one of the switches you see here will leave that scheduled traffic that is supposed to be arrive on time to the listener, the destination. To do that, then that traffic has to leave egress each one of the switches on a specific time, and should not be delayed. It's like a train going from one stop, one station to the other, arrive on time and leave on time. So that at the end it will arrive at the destination on time, because people are waiting for it in every one of those stations. So how we can make that happen? Of course, conventional Ethernet doesn't have any provision to do that. And of course, to make sure that the traffic will arrive and leave on time, especially that traffic that factory traffic, for example, not maybe audio video, factory traffic, to ensure that this is the case, then all these switches need to be time synchronized, need to use one time reference. And that is why IEEE 802.1as is needed in a time sensitive network. So to how the switches will do that, you have to compute a schedule, and the schedule will be pushed down to the switches. We'll see how this schedule will look like, but the schedule is defined in collaboration between the engineers. It's not really dynamic, or all software or hardware. Some engineers will be involved, although in the distributed configuration models that IEEE 802.20 task group is working on can make it all automatic, because if you distributed model, you can use stream reservation and compute everything dynamic within the network, which has the added advantage where you can compute the schedule dynamically, and even cope with situation where one device goes down, one link goes down, or change the configuration, which is a limitation in 802.1 QBV. You can read yourself when I send my slides and put it in the wiki. You can read the steps, but the whole idea is that the CNC will get a topology first using LLDB, and will get the link delay for each link using some method. It can be 802.1as, because 802.1as can help compute the link delay for each link. And it also uses the CUC will talk to all the clients, the listeners, and token, got all the configurations, their bandwidth requirements, their stream characteristics and requirements. Will get all of this information and give it to the CNC. CNC will have the topology, will have the link delay for each link, will have also can compute the route for each the stream characteristics and bandwidth. Can also compute the route and can help reserve the required bandwidth by maybe communicating with the stream reservation protocol, which is IEEE 802.1q So at the end of the day, CNC also compute a schedule, and the schedule we'll discuss it later. But the schedule will be pushed into each one of those switches along the route or the path that will be used by a given stream. Now let us look at how the schedule works in action for 802.1 QBV. So this is an animated slide. So in 802.1 QBV, which is time-aware scheduling or shaping, so each egress interface will have queues, of course, and frames are placed into these queues based on their priorities. Remember, this is layer 2 network, so we'll use the 802.1p priority field, the 3-bit priorities to do that. If you are using layer 3, like .NET, which is defined by IETF, you can use def server component. And then the schedule that is pushed by CNC into each one of the switches will have something called gate control list, like the one you see it here on the right. And the gate control list is divided into windows, like window to 0, T1, T2 to 3. And each window, of course, will have a size, and time, this time duration. So the number of windows and the duration of the whole list, which is a cycle, like you finish the list, you finish all those, you go from T0 to 0 to T1 to 2 to T3, and then you go back to 0. The frequency of doing this, as well as the duration of between T0 and T3, is all configurable, and configurable based on the needs of all of these streams, and it is done by CNC. So all of those gate control lists in all the bridges that are pushed into
But
this
Hisham,
yes.
but
Go ahead,
this is kind of equivalent to, for example, the same thing with in PTP exists in entity called PTP profile. So in this standard, for example, the granularity should be defined in an external document or a contract in order to make it interoperable. Otherwise, there is no meaning. I mean, if, for example, if the time window is 1 hour, everyone supports it.
Exactly. So I'm saying T0, T1, the duration for each one of those windows, the frequency of the cycle, the duration of the cycle is all configurable based on the needs of all those listeners and talkers, and those listeners and talkers communicate to CUC these needs using some interface which is outside the scope of the standard. If you would like to learn more about all of this, you can read IEEE 802.1 QCC standard, which is published last year. And it defines all the enhancement of the stream reservation protocol, as well as how the QCC gets what information it gets from the talker and listeners, but it doesn't define the interface or the protocols to do that. One protocol defined by the industry, although it's not mandated or even described in IEEE, is OBCUA, but that's one protocol. The key thing here that I would like to mention, all of these gate control lists need to be synchronized. Like exactly what you mentioned, Gilad, is that you cannot have T0. They have to be synchronized. Other maybe one guy wait for an hour, the guy wait for half an hour. That doesn't work. They all have to be synchronized. Like the train arrive here at 10 o'clock. It should leave at 10:05. Then the next stop, it should maybe leave at 10:30, because if we don't do that, maybe ultimately it will not arrive at the right time at the final destination. So all of the definition or the specification of all of those gate control lists need to be synchronized, and to allow that synchronization to happen, we need .1AS. That's why .1AS is needed. I would like to bring your attention that in the car, you might not want to use QBV. There is an alternative protocol. It's called IEEE 802.1 QCR, which got ratified or approved recently. And that QCR does not use all of these gates, but within the car, it is suitable and it doesn't need time synchronization. But I would like to focus the discussion here at least on QBV, because it shows that shows the need for time synchronization using .1AS. There is important rules that are followed by QBV, which is a frame from any queue cannot be sent or transmitted until the gate of that queue is open. And when you open the gate, the frames, and if you have more, if the gates of more than one queue, if in any time window like time T1, three gates are open for 3 queues, then all of them can transmit traffic. The traffic will be transmitted in a strict priority manner. What if the gate and a frame in one of those queues will not be transmitted if the remaining time until the gate is closed is not enough to transmit that frame? We'll see this during the animation. If I have more than one gate open in a given time window, then all of the frames within and all of these queues will be serviced in a strict priority manner. So let us, so first step, 802.1as is important to allow time-aware shaping across all these bridges to work. It's fundamental. Without time synchronization, we can't synchronize arrival and departure of frames from all of these queues to in any bridge to arrive at the final destination at the right time and meet their deadline. So let us now go to time T0. On time T0, you see the frame in Q4 is transmitted and the other gates are closed, so none of the frames will be sent. Do you see the animation? Hello?
Yeah, we could see it. It goes back fairly quickly, but I could see it.
Good. Now we finished T0. Let us move now to T1. For T1, look at the frames from Q3 because it has the highest priority, and then Q2. But the frame in Q1 will not be sent because it's closed before the gate is closed before the gate is closed because the time allocated to it is closed. But when we move to T2, where Q1 gate is also, let me go back here. When we move to Q2, when we move to T2, Q1 has a frame which was not sent during T1 because time finished before it can be sent, so it has to wait. But when we move to T2, it will be sent. And nothing in Q2 will be sent. The frame in Q1 is sent already. When we go to T3, all of them will be closed. Nothing will be sent, and then the cycle repeats. So you see from this animation how the frames are not serviced in a strict priority manner, like what you see in regular switches, using weighted for queuing or weighted round robin, and all of this. There is a gate. They are transmitted, or the scheduler transmit a frame based on gates. Gates open, you transmit the frame. Gates closed, you can't transmit it. Gates open, you transmit the frame if there is enough time for that frame to be sent during the time window where the gate is open. So the one thing I would like to discuss with the team here.
Sorry, question here.
Yeah, sure.
Does the standard support, for example, dropping the frame if it did not make it in the time when the gate was open, or does it just wait for the next occasion for the gate to be open?
Very good question. I think based on the example you have seen, it doesn't drop frames.
There is a different standard in TSN 802.1 QCI that on the ingress port, it does filtering based on arrival time.
Yes, the QCI filtering and policing, yes, but that is not what I am discussing here. This is the Shaper QBV. The one thing I would like to mention, one important thing that TSN does, which is zero congestion loss. For all these frames that need to meet specific deadlines, the way to achieve deterministic latency and deterministic arrival is to avoid congestion loss. So you cannot drop frames. That is essential to make this deterministic networking work in TSN. The mathematical proof of this is beyond the discussion here. If somebody is interested in mathematical proof, I can prepare a presentation for it. But for now, just it suffices to know that zero congestion loss is really how TSN achieve deterministic latency. So what I would like to discuss with the team here is a deterministic data center. So I'm sure you are aware of IEEE. There is TSN in layer 2 in IEEE 802.1, and there is a corresponding one in IETF called DITNet, which really is looking at how to support deterministic network in a larger scale IB network. So there is work already that has started on IEEE 802.1 to allow DITNet to use the quality of service traffic management tools defined in IEEE 802.1. There is already a specification to do that, working on one to do that. Why? Why did not use different shaper police? It can use the same at layer 2. So, and this is really the whole idea. But the whole topic of integrating TSN tools with DetNet is subject to lots of research. For example, if you look at many of the protocol, if you look at many of the protocols or tools defined in TSN, like QBV, CR, QCR, and others, you have to ask the question, are all of them suitable for large-scale deterministic network? Yes, all what IEEE.1 TSN task group is saying to guys in DetNet, use the tools defined by us. Why define your own shaper? Why define all of this? Use our. But the question is, which one is suitable for large-scale network? This is an area for research. I myself, I collaborated and I co-authored 2 papers about this issue, and you can look at this paper. I give you references here. One of the paper, we looked at 40 algorithms, 40 tools, and we found out that out of the 40, maybe 2 or 3 are good for large scale networks. So this is an area for research that we need to look at. But deterministic data center is important, because if you have deterministic data center network, then in application like IoT application with edge computing in a factory, for example, to have end-to-end deterministic networking, it is better to also to have deterministic data center network. Then the whole end-to-end path will provide you deterministic networking. But if you use deterministic data center networking, then which protocol you use for time synchronization? I think we are defining a profile right now, and the work is led by Michelle.
Yeah.
And the
Michelle
question
is,
now, can we take advantage? Go ahead, please. Go ahead.
Yeah, I was going to ask you why Michelle is not available now, but what are your thoughts? What would be the main focus area for the data center PTP profile in discussion, the TAP data center profile in discussion? Where would be the points of focus in your mind, Hisham?
I can't hear you well. Is this the question?
Yeah, the question is for the TAP PTP profile we're working on. What are the in your? So I'm trying to understand what are the points, major points you're pointing to that you're highlighting to be worked at.
Yeah. So
what
I think the question is,
this is let us highlight and wait.
Yeah, I think your question is, when we define the profile for the data center, what can we incorporate into this profile to support deterministic data center?
Yeah.
Or how we can benefit from what is being done in .1 AS to define the profile for our for the data center project.
Yes.
I think this is the question. That's a good question. I like to think about that. I can't answer the question right now, but that is something I would like the team to work on or to think about.
So after the OCP Tech Week, everybody is heads down for the next week. But after that, we will initiate the work stream group meetings, and we are looking, Hisham, for you and others to participate in this think process, and also in the work process. We will rely on everybody here to make the necessary progress.
Exactly.
I would like to hear your thoughts about it. I was hoping there's going to be, we'll be able to discuss it today, but definitely we can do it at a later time.
So
yes, absolutely.
Yeah. So Hisham, this is Alon again. Sorry for
Hi, Alon.
First of all, this is a great presentation. I do want to say that that even ignoring all the TSN components, 802.1 AS has certain things that we should consider. And I was actually thinking of making a presentation that compares different PTP profiles. But
Yes.
one of the big differences between 802.1as and other profiles is that what it calls a boundary clock is very different than a boundary clock in traditional 1580. It's kind of a hybrid between a boundary clock and a transparent clock, and some of the approaches from there I think would be useful to make I'll call it a simple boundary clock that could be implemented inside a switch that could support multiple clock sources at the same time without needing a PLL for every clock source.
Excellent. I just mentioned this actually later. Very good point,
Yeah.
Long. I would like to bring it to your attention, the attention of the team, is that the definition of IEEE 802 v2, 2019, which got released last year, that's some of the stuff that was defined in IEEE 802.1as. For example, if you look at IEEE 802.1as, they have this media-dependent and media-independent architecture. The architecture for time synchronization divides the functionality for time synchronization into media-dependent and media-independent. That wasn't an that type of architecture wasn't an IEEE 802, sorry, IEEE 1588 v2. Now it is part of IEEE 1588 v2.1 or 2019. Similarly, and I will get to that in my presentation, there are features that are defined in IEEE 802.1s revision, which got published this year, that was incorporated into IEEE 1588 v2. But there are features, I agree with you, like that architecture, media dependent, media independent, and other features I will mention later. We can add them into our profile for the data center. And since deterministic data center is something I think it is very useful for many applications related to cyber physical systems, like IoT applications, for example, and edge computing, then we need to add features in .1as that can support deterministic data center. By the way, there is a paper also that I published last, maybe 2 years ago, I don't remember, provide very comprehensive survey for TSN and all tools and everything, including and also application for 5G. And I provided a link to it or reference to it in previous slides. It will give you lots of information about this. It's almost 60-page paper, so it's useful for the team here to find more about TSN and .NET. So now we finish this very, very brief introduction about TSN, and we establish the need for .1as, which is generalized PTP 1588. And since Long and others are already involved in TSN, if you recall, .1as project started some time ago because of the need for time synchronization in layer 2 Ethernet network. And later, the first release of it, first specification was released in 2011. And it actually supports, has a profile, 1588 v2 profile, because 1588 2019 wasn't there. This was 2011. So it uses 1588 v2 profile for Ethernet, full duplex Ethernet. It doesn't have a profile for other 802 compatible LAN like 802.11. Profile by complete definition of a profile as defined in 1588, but it provides some specifications and protocols to support time transport .11, like the find time transport .11, and using and define the transport of time for EPON, and for CSN, coordinated shared networks like MoCA, which is multimedia over coax, or GHN, which is used, defined by ITU to transport Ethernet over coax. So there are specifications on how to transport the protocol, but not complete profile. A complete profile is for full duplex Ethernet. Later, after releasing .1as in 2011, we worked on .1as Rev revision. And the revision, the main thing that was added into that revision is multi-domain. Multi-domain was in 1588 v2, but was not in first release of .1ES in 2011. They only have one domain, which is domain 0. In .1ES Rev, we added multiple domains. There was domain 0, and you cannot change it. It's number, it's still 0, and you can have other domains, and we'll talk about that later. So this is the brief history of .1ES. .1ES Rev released this year in 2020. So .1ES, as Long mentioned, when it was originally released in 2011, has benefits that we can incorporate in our profile for the data center. First of all, it uses a free running clock, which uses very low cost oscillators, which is commonly used in industrial automation and in-vehicle automotive applications. So that's good because it saves cost. I'm sure we are defining a profile for the data center, and our definition is not just for industrial automation. It might be for other application, but at least we can use this feature when we use the data center for industrial automation. Also, it has improved reliability, and this happens in two ways. Number one, .1ES mandates that all the switches or the bridges or the time-aware bridges or time-aware devices, including edge systems, but should support the protocol. And in .1ES Rev, it was mandated that if a device doesn't support the protocol, it will be taken out of the network. It will be precluded. When I say taken out, it is taken out of the whole transport of time information. 1588 allows such a kind of switches. They can put a switch which doesn't support the transport of that protocol, and it can be used to transport some other traffic, as usual, like any other bridge, but that is prohibited in .1ES, and this simplifies the network, and also allows the convergence of the whole network when we run the best master clock algorithm, which we'll discuss later, converge quickly, and also having this kind of switches which is do not support the protocol will introduce extra jitter, wander, and that may cause the whole system might not be reliable enough and work as reliable as it should. So I think we can incorporate in our definition of our data center profile mechanisms like the peer delay mechanism, which we'll discuss later, to discover, for example, that for a switch to discover that the switch it is talking to can support the protocol or not, and if it does not, you can take it out. So there are these mechanisms used by .1ES. We can use it also to discover who supports the protocol and who doesn't, and if somebody does not, we can take that switch out. So this kind of feature we can look at when we define our data center profile. There is a comparison here between the .1ES profile versus 1588, only for full duplex Ethernet. We don't have a profile for anything else, or something I can call it a profile. So there are many things here. I don't know whether we have enough time to go each one of them because I have other material that I need to cover. So right now it is 11:51. I have 9 minutes and I have many slides, but I think you can read this slide later. It is based on .1ES. You can read .1ES. The one thing I would like to mention is that .1ES 11 uses two-step. .1ES 2020, Rev 2020, does not preclude using one step. And there are many things really that this profile. For example, we use SNMP for management. There is nothing, and we started to work and we started to work on netconf and Yang recently for management of .1 AS after the releasing RIF 2020, because 2020 does not preclude using netconf and Yang. So we started by SNMP first. Now we are working on netconf and Yang, but it doesn't exist yet in 2020. It will be. We are working on it right now. So you can read this because I have to cover other material. And then there are some performance requirements for .1 AS. For example, the B delay turnaround. If you look at all of these performance requirements and you can read them, they aim at ensuring things are done quickly. Time synchronization is done quickly. Things are done fast, and the whole thing is done in a reliable manner, which is exactly what we need in a time-sensitive network. So you can read this. If you have questions, please let me know. So this is an example of a time-sensitive network or .1 AS network, which shows a synchronization hierarchy. And look at all of those endpoints. They have clock master interface and clock slave interface. The clock master sends the clock, and the clock slave try to synchronize with it. And of course, endpoints have a clock slave interface. They don't have a clock master because clock master is the one which is send send a message which transports the protocol. Everybody tries to synchronize with the grandmaster protocol in a way. I will describe it later, but it's important to know that when a switch or a bridge receives a .1 AS message from slave board, it doesn't forward it right away. It has to do some processing. It has to compute the residence time, for example, before it's sent it to, and other things before it's sent it to the downstream switch. So this is a synchronization hierarchy, and that network was ports designated as slave, master, whatever. This network, if you look at it, it's like spanning tree, but it is .1 AS spanning tree, not, for example, the rapid spanning tree defined by 802.1d, which replaces the old spanning tree defined by Radia Berlman. So the best master clock algorithm, I think I don't have to go through it in details. It is, if you recall the Bully algorithm in distributed systems, it is similar to this one. So it uses announce messages, and people send announce messages to each other with information data like priority, clock class, clock accuracy, and clock identity. And there are tables to define the priorities, the classes, and accuracy and identity. Identity is like MAC bridge, for example, not MAC address. And in each switch to compare those information against what he has and against the information received from other announcements. And when they exchange this information, they find out who is qualified to be the grandmaster. When the grandmaster knows it is the grandmaster, it will be the only one that send the announce message. It will be the only one send the announce message. It will be the only one send the announce message to everybody announcing victory. I am the grandmaster.
It's a 4-minute warning. Let's see that we cover the last.
Yeah, so I think I can skip all the slides. You can read about how is the difference between the BCMA defined in .1 AS and the one defined in IEEE 1588. For example, 3 main differences are key, like there is no foreign master qualification. You receive a message from the master, it uses it immediately. You don't have to do some qualification procedure that is defined in 1588. There is no pre-master state. There is no uncalibrated state. You can read all about this in 1588. We eliminated all of this because we need things to be done quickly. We don't want it to slow things down. So when we define our MCA for our data center profile, we can use these features when we define our own BCMA and we can adopt this feature and I think it's a good idea to adopt them, especially if we are shooting for something like deterministic data center. And Elad, I think I have slides now to talk about propagation delay measurements and other things. Do you think we have time to go through them, or we can delay this to next time, or whatever you decide?
Yeah, choose one more. We can fill the rest of it out. Choose one.
Yeah, I think this slide talk about peer-to-peer delay mechanism, which is used, and not the delay request and response mechanism. We use the peer-to-peer delay mechanism, and in .1AS. And if this is you can find this whole algorithm or mechanism used in many systems. We used it in EPON, for example, by MBCB to define for the TDMA algorithm. So, and at the end of the day, you will find this equation tell you the link delay, and it assumes that the delay is the same in both directions, which most of the time is true, but sometimes it is not. So really what it defines is the mean delay, mean link delay. And for the sake of our profile, which is for full duplex point-to-point Ethernet link, any asymmetry for the delay between the link from A to B and B to A is not accounted for. We don't care. We ignore it. But when I work, for example, on the delay transport in DOCSIS, in HFC network, there is asymmetry, and we have to account for it. But here we don't have to for this profile. Again, so asymmetry is one source of error. The other source of error is really the assumption is which clock frequency we use, initiator or the responder, and that we have to make it, or the grandmaster, which clock frequency we are basing our link delay measurements on, and that has to be determined, and we have to make that decision. Again, the text here is from .1AS. You can read it. If you have questions, please let me know. And then we use one of the things also that we can adopt in our profile is that in .1AS, synchronization or frequency synchronization is not done by physical adjustment of the clock, because if you use VLL, for example, that will be very slow, and there is a problem for the gain peaking. There is a gain peaking effect. So there is something defined by .1AS which we can adopt called logical synchronization, and the equation that can synchronize the time at some point with the time at the same point in the grandmaster. This equation is used, and I would like to go through it, but we don't have time. Yeah. But the logical synchronization is good because it allows you faster convergence, and it also avoid all this effect of gain peaking.
I think we'll touch lightly this subject of synchronization in the Tech Week. So yeah,
so it's up to you, Elad, to go through the details here. And
our time is up.
Yeah, so the only thing I would like to discuss maybe later is the domain, multi-domain. And multi-domain really, this is the last slide, is very useful for some application, like in industrial automation. Some application would require to have a whole domain for the whole factory, but maybe for some devices you can have a working domain which has its own random master, because every domain has its own master, and the bridge can participate in both domains. So that is one reason for multiple domains. The second one is reliability, because you can have two grandmasters in hot standby, and each grandmaster has its own domain, but they are both working, and maybe you can use redundant links defined in 1588. And if one master goes down, you use the hot standby grandmaster. But I would like to bring the attention of the team that full definition of redundancy and reliability using multi-domain is not done yet in .1 AS Ref 2020. That is something we are working on right now. So using hot standby is a new project in .1 AS. I think multi-domain with hot standby can be a very good feature for our data center profile. I'm done. Thank you.
Thank you. Thank you, Hisham. Thank you. This was a really great presentation. Thank you for walking us through the TSN IEEE specification. We obviously want to leverage on that in TAP, and we look forward to see your contributions and your involvement in the PTP workstream. So that goes for everyone here and your colleagues. If you wanna be involved, if you wanna get involved, please reach out to Michelle. The information is on our wiki webpage.
Yes, I will send it to Kevin. Kelvin, he asked me yesterday, but I will send it to him today. He can put it in the wiki. And if anybody has any question, please don't hesitate to send me a question. I see many questions here, but I cannot answer them now. Maybe if somebody can collect them and send them to me, I will answer them in the email.
Sure, I will do that.
I'm sorry I overlooked the many details, but the time is very limited.
Right. Thank
It was
you,
a great,
Hisham.
it was a great presentation.
Thank you very much.
Thank you, Hisham.
Looking forward to work with you also on this. We have lots of challenging and interesting work ahead of us. Thank you.
Absolutely.
Yeah, thank you.
Any other questions? Okay, we'll close it off for today, and we see everybody next week.
Everybody, when you
Okay, bye-bye.